Okay, welcome back. Today we're going to be continuing on our introduction to the atmosphere, and the focus is going to be somewhat on chemistry, basic chemistry. Um, I know none of you have taken the formal chemistry class yet, but having a at least superficial understanding or foundation of chemical composition, the structure of molecules, and the phases, such as solid, liquid, or gas, that all matter can appear in here on Earth. I'm hoping that you are familiar with the three main phases of matter here on Earth, and a fourth phase of matter that is actually the most common in the universe, yet the least common on our planet, which is known as plasma. Plasma is not a solid, not a liquid. It's close to a gas because it has expansive capabilities. It does not take on a specific shape, and it actually emits light and other wavelengths of energy. Many of you have heard that the sun is like a big ball of gas. Technically, it's a big ball of plasma, which is similar to gas, but it is not actually a gas. So, that's some of the physical properties of chemical material. Okay, so I know we left off on the last lecture at the envelope of gases that surround the planet, and that is the atmosphere, which is the focus of the rest of this unit. And the atmosphere is something that is probably the most dynamic characteristic of our Earth system, as the atmosphere changes moment to moment. The difference between nice still air that we're feeling right now, or that I am, there's almost not even a slight breeze. But if a cloud moves in between my location and the sun, the temperature will drop just a little bit, making the gases of the environment locally contract, become more dense, fall downward in altitude, and subsequently cause wind to move around. So it's a very dynamic system. As the sun rises or appears to rise higher in the sky, we start to see temperatures or the measure of heat energy increase. And that too can cause wind as a result of density differentials. Hot air is much less dense than cold air, and that's why hot air rises, cold air sinks. Simply because of density. Hot air and cold air could be made of the exact same chemical components, but hot air, any given mass of hot air, takes up more space than that same given mass of cold air would, because the cold air is literally compressed, making it more dense, taking up less space, but having the same mass. So the reason why a hot air balloon works as it rises up over the land is because the air inside the balloon is taking up more space than the same amount of air outside of the balloon. So having the same mass inside the balloon versus outside of the balloon, but taking up more space, lowers the density, making it rise up in altitude. Okay, so the atmosphere is a gaseous envelope, and here we are, we have some wind now. The thickness of the cloud cover overhead is variable, and the less sunlight penetration that we get due to thicker cloud levels, will fluctuate the temperature and the density just enough to keep air masses moving. We don't see so much movement in the lithosphere, the crust, because it's primarily solid. And we don't even see so much movement in the hydrosphere, at least in the oceans, comparatively to the amount of movement that we see in the atmosphere. The atmosphere is dynamic. Okay, so the last slide from your PowerPoint download was slide number 6, and that had to do with land, water, and air. And it was the air, the atmosphere, that I had introduced to you. So I'd like to move on to the next slide, and I believe Kevin is one of my dogs. I believe it is a brief section review. And it is a section review. So I'll go over the 4 questions with you. You have them already, and perhaps, hopefully, you've already tried to answer them. And I'm just going to clarify what those answers would be. So the first question is, what are the 3 main features of Earth? And what I mean by that are, what are the 3 spheres that we're studying in this unit? The 3 spheres are the lithosphere, the crust, lithos, rock, sphere, 3-dimensional circle. The hydrosphere, water, which is the oceans, lakes, rivers, streams, polar ice caps. And the atmosphere, the gaseous envelope, which goes from ground level all the way up to really space. So the 3 spheres, in short: lithosphere, hydrosphere, atmosphere. Pretty simple. Okay. The second question concerns the hydrosphere, the water sphere. What % of the hydrosphere is fresh water? 3%. 3% of all of the water on the planet is fresh water, meaning the remainder, 97%, is salt water found in the oceans. So the percent of the entire hydrosphere that is fresh is merely 3%. Remember from the last lecture session, most of that 3% of fresh water isn't even available for us to use, never has been. That is why? Because it's frozen. Alright, so the freshwater component of our hydrosphere, very, very minute, yet it's all of the fresh water that any organism has ever had access to since the dawn of life on Earth 3.7 billion years ago. There's no less fresh water now than there was then, and there's essentially no more fresh water now than there was then. Okay, to move on to question number 3, what % of the hydrosphere is available for drinking? So, in order for water to be drinkable, 1, it has to be fresh water, not salt water. 2, it has to be liquid, not solid or gaseous. So the % of the hydrosphere that's available for drinking is less than 1% of all of the water available on the planet. Less than 1%. All right. Because we know 3% of the hydrosphere is fresh water, most of that is frozen, it leaves us with less than 1% of the entirety for available drinking water. And I alluded to the importance of conservation last week in regard to treating fresh water as though it is the most vital resource available to us on the planet, and it is. Without fresh water, we don't live. Without fresh air, we don't live. So the atmosphere in conjunction with the hydrosphere are really the most important aspects of our Earth system in terms of supporting life. Okay, and then number 4, the last question of this section review: what is the envelope of gases that surround the Earth? Atmosphere. The atmosphere. Pretty straightforward. Okay? Now, the atmosphere, as stated, is dynamic. It's always in motion, and it fluctuates in terms of temperature, how much heat energy is in any given part of the atmosphere at any given part of time, how much water vapor is dissolved within this gaseous envelope at any place at any time. That will affect humidity, cloud cover, whether or not we'll experience some form of precipitation, at what temperature will dew form on the grass or surfaces overnight into the morning. How much does the local environment cool down as the sun sets? And how much does the local environment warm up as the sun appears to rise and track across the sky? These factors are determinants as well as reactions or resultants of energy addition or subtraction. And we know energy on Earth, I'm pointing up, comes from the sun. All right? Now, our atmosphere has been in constant change since its origin as right after the Earth's initial formation from the nebula that formed our solar system. The sun, the 8 planets, including Earth, and the asteroid belt, and the Oort cloud, and all of the other huge and maybe not so huge objects that we share literal space with. Okay? The atmosphere has always been in a state of change. It has evolved over time to contain different ratios of gases and different gases altogether. I know you are familiar with at least a few of the gases that we rely on or interact with on a daily basis. Oxygen, gaseous oxygen for one, super important. Gaseous carbon dioxide for 2, another very important element, I shouldn't confuse with element, another important component of the atmosphere. But there are other gases like nitrogen gas, N2, and methane gas, CH4, and water vapor gas, H2O, and a myriad of other chemical compounds in the gaseous state that reside in our atmosphere. And these gases cycle in and cycle out depending on activities and life on the Earth. There are cycles. There are some organisms that absorb certain gases and expel others by a simple method of metabolic transitions. We breathe in a collection of gases, but our our bronchial lining, our lungs, will filter out the gases that we need, primarily oxygen, out of that atmospheric mix that we inhaled, and then we exhale basically that same atmospheric mix minus some of the oxygen that we were able to absorb. So we're always in flux in terms of what's in the atmosphere, what we take out of it simply by breathing. But other organisms, like plants, they carry out respiratory activity, but they use different gases. The plant doesn't take in oxygen and release a higher concentration of carbon dioxide like all animals do. Plants actually take in the atmosphere and use the carbon dioxide, break it down metabolically through photosynthesis, and expel a greater percentage of oxygen than what they absorbed. Than what they absorbed. Turn you back upside down here. By breathing it in. All right, that's Kevin. We're gonna have to just adjust the angle here a little bit because my home studio is janky. Okay, so let's click forward to the next slide. All right, Kevin. Kevin's going to exit stage right. Oh, Lord, this is a mess. Okay, so clicking to the next slide, we're going to discover, the ancient atmosphere. Okay, the ancient atmosphere is very different from the atmosphere that we know of today. Now, how do we get information about conditions of ancient atmosphere when we know that no one was around to observe them? 4 billion years ago, when the Earth's crust finally solidified, there were no organisms to interact with the environment. There were no meteorologists. There wasn't even a fossil trace of life 4 billion years ago, when the Earth cooled enough to start to have gaseous water vapor condense and start to form lakes and streams and the oceans. The atmosphere itself was made up of different molecules, different combinations of atoms that really resemble nothing to what we see as the atmosphere today. The ancient atmosphere was primarily composed of ammonia, water vapor, and methane. Now, none of these gases, ammonia especially, are good for organisms' respiration. Ammonia is poisonous. Ammonia will kill you if you ingest it, even if you waft the fumes of volatile ammonia, ammonia evaporating out of a cleaning solution. That stuff closes up your lungs. It burns your respiratory tract. It would cause suffocation and, in some cases, irreparable damage to your lungs and linings of your trachea. So, ammonia, super toxic. Ammonia is a molecule composed of nitrogen and hydrogen. When elements are combined in specific ratios, the combination of elements no longer resemble the individual elements' characteristics before they were bonded into a larger molecule. Let me give you an example how this chemistry stuff works. Hydrogen, typically in the environment at room temperature, hydrogen, the most simple atom, a single proton and a single electron, hydrogen is a gas. and hydrogen is an explosive gas. Okay? Oxygen, a nucleus of 8 protons and 8 electrons whirling around the outside, at room temperature is also a gas. So you take, and oxygen is also explosive. So if you take hydrogen and oxygen and stick them together, the hydrogen atoms and oxygen atom, H2O, 2 hydrogens, 1 oxygen, they bond to form a molecule of water, H2O. And interesting, water puts out a fire. So you take an explosive gas, hydrogen, and an explosive gas, oxygen, put them together at a ratio of 2 to 1, H2O, and the resultant molecule or compound has none of the attributes of either of the 2 ingredients that made it up. Explosive plus explosive put together now act as an extinguisher. It's pretty interesting. Another compound that you're all familiar with, table salt, sodium chloride, right? NaCl, salt. It's pretty delicious. Adds a little flavor to most recipes. Salt in itself is not poisonous or explosive, but the 2 elements that make up salt, sodium and chlorine, are both pretty toxic. Sodium is a metal, and pure sodium, when exposed to water and oxygen, spontaneously combusts. It's a metal that literally bursts into flame when exposed to humid air or dropped into a container of water. And chlorine, we know, is the active ingredient in Clorox, bleach, sodium hypochlorite, the stuff we add to swimming pools, the stuff that is added to your drinking water to prevent microbial and fungal growth. So chlorine, toxic, sodium, explosive. You mix them together at a 1-to-1 ratio, Na, sodium, Cl, chlorine, sodium chloride, you now have salt. Sprinkle it on your food, it's delicious. It doesn't explode and it doesn't kill you. So when we look at compounds or molecules, they no longer characterize the specific nature of the elements from which they are composed. Pretty cool. Okay, so ammonia gas is nitrogen and hydrogen, NH3. There is 1 nitrogen atom and 3 hydrogen atoms bonded together to make a molecule of ammonia. Super toxic. Nitrogen's not toxic. Hydrogen's not toxic. Put them together in the ratio that forms ammonia, and you have supertoxin. The ancient atmosphere was primarily ammonia. Not good for life. The secondary component of the ancient atmosphere is water vapor, H2O, in its gaseous state. That is because the ancient environment was quite a bit warmer when the surface of the earth was still partially molten. We had the not low enough temperatures to allow for water vapor to condense into liquid water. So all of the H2O on the planet was gaseous, floating around as part of the atmosphere. And some of it still is gaseous, as we'll see in the water cycle. Sorry about my hand there. The fact that my studio fell apart mid-lecture was not very helpful. Anyway. Dogs. So, the third The third, stop. The third primary component of the ancient atmosphere is methane. And methane we see now added to the atmosphere from the breakdown of vegetation. But back in the ancient early formative years of the Earth, there was no life, there was no vegetation, and there were no herbivores eating that vegetation and breaking it down. So methane naturally formed out of carbon and 4 hydrogen atoms. So CH4 is methane. I do want you to be familiar with the chemical, what do we call them? The chemical formulas of these simple molecules, such as ammonia, NH3, water vapor, H2O, and methane, CH4. Methane has a somewhat of an offensive smell to it. If you ever drive by a farm that has livestock and you smell that manure smell, part of that is methane. There are some other mercaptans, sulfhydroxys, and such that add to the, stink. But methane is pretty evident. You can smell it. If you've ever driven out or been out near the beach, as you approach within a few miles of the beach, you're in the wetlands, the marshlands, and there's that sort of rotten eggy smell that says, we're near the beach. Phew! That's methane gas, and that's as a result of some of the marsh grass decomposing and turning into marsh gas, which is methane. So the ancient atmosphere had ammonia, water vapor, and methane as its primary components. As time goes on, 500 million years, 500 million years, pretty long for you and me, pretty short for geologic time. But as time goes on, the sunlight, the energy from the sun, the wavelengths of ultraviolet and infrared radiation naturally broke apart these molecules of ammonia and the molecules of methane and freed up the atoms, the components that made up those molecules, and allowed them to rebond in different ratios to become less toxic and more friendly to living organisms that will eventually show up in the fossil record. Sunlight broke down the poisonous gases into hydrogen gas, H2, nitrogen gas, N2, and carbon dioxide, CO2. Okay? You notice a lot of twos. Many atoms bond with one another, forming a pair of those atoms, which would make a molecule. So, hydrogen gas is actually 2 hydrogen atoms bonded together to make one hydrogen molecule, H2. The 2 denotes 2 atoms of whatever letter precedes it. Nitrogen gas, N, the chemical symbol for nitrogen, N2, the chemical formula for nitrogen gas. 2 nitrogen atoms make 1 nitrogen molecule of gaseous nitrogen. And we'll see their importance here in some of the metabolic, abiotic to biotic cycles we'll study in the atmosphere. And the last one, the last term, last words of the last sentence of this last slide is carbon dioxide. Carbon, chemical symbol C, oxygen, chemical symbol O. Combine them in a ratio of 1 carbon to 2 oxygen atoms, and you get CO2. CO2 is carbon dioxide, and that plays a crucial role in the next step of life evolving on Earth. We'll look at that next time. Feel free to review this. I'm also going to send you a new set of atmosphere PowerPoint slides to get us up to speed for the next few lectures. All right, talk soon.